Hello. So I wanted to talk about Little's Law and then its applications. So, when we talk about process, I think it's inevitable to talk about Little's Law. And I want to start with two quotes. One is by, Dr. Eli Goldratt, and he's the author of The Goal, which is a very popular process or operation management and book. This is a novel, but it's a novel talk about a series of constraints. So it's quite interesting, right? If you have a time, I highly recommend you to read it. This is almost a must read for any MBA programs in United States for operation management, because when they talk about operation management, this is a good book to read. Okay. Dr. Elia Goldratt said that complex solutions do not work. The more complex the problem, the simpler the solution must be. Okay. Another quote by Albert Einstein is, any intelligent fool can make things bigger, more complex, and more violent. It takes a touch of genius and a lot of courage to move in the opposite direction. So I think Little's Law really fits those quotes really well. Okay. So, when we talk about process, actually any process is a queuing problem. So when you see, in the airport, there's passengers lined up, and at a coffee shop, customers are waiting for their orders. This is a queue, right? It's a waiting line. So any queuing problem, we say that we can analyze it through a more kind of scientific approach. And any production system, you look at this, I have some picture here, right? Those are, production systems, and it's a queue as well. So any queuing system essentially takes a arrival behavior, right? And then a departure. So customer coming into the system, and then within the queuing system, item in queue or item in service, and then these items will depart from the system. Okay, so essentially we see those arrival and the departure as a flow of items through a queuing system. Within queuing system, we have three major elements here. The average number of items in the queue, in the queuing system, right? We denote with L. And then lambda is the average number of items arriving per unit of time. And W is essentially the waiting time in the system for an item. Okay, so this is the Little's Law. Very, very simple, right? Deceivingly simple, but it's very, very powerful. So deviated from the traditional queuing model is that we do not consider the distribution of arrival, distribution of a departure, all those detailed, all those technical detailed. We simply count the average number of items in the queuing system, and the average waiting time in the system, and then the average number of items arriving per unit. Very simple three elements. Okay. Now, this is named after a MIT professor. I have his picture here, John Little, right? He is the first person mathematically prove this Little's Law is a correct form, right? And he is a professor at MIT's Sloan School of Management, and he proved this law in 1961. Basically, the law states that the average number of a customer in a system over some interval is equal to their arrival rate multiplied by their average time in the system. Okay, so now let's look at an example. How can we use this Little's Law? Let's say that we are at a coffee shop. Over the course of several months, you visit this coffee shop at a random time between 6 a.m. and 9 a.m. You observe the queue waiting time, average about 10 customers, and then that it takes you about 3 minutes to get in and out of the shop. So if I ask you how much money is this coffee shop making, you probably say, I don't know, right? But applying Little's law, you actually can calculate it. Now, of course, we needed to do some estimation for sure, right? So let's just say what's my working process, or what's the my waiting line system, right? There are 10 people. Okay, what's my cycle time, which is the uh, 3 minutes of in and out time that you use, right? And then the throughput essentially is applying the Little's law is equal to 10 divided by 3, which is 3.33 person per minute, and that translated into 200 people per hour. So to get an estimate, for sure, we needed to to get an estimate of the revenue, we for sure needed to make some assumptions, right? So assume every customer will spend $8, and then the 200 customer per hour is 1,600 per hour, and depending on how many hours the shop operates, and then also you give some kind of leeway, which is accounted for peak time and non-peak time, you can come up with the daily revenue that companies generating. And then with also additional costs estimation, you can estimate that their profit, right? So that's a very useful tool for analyzing a shop operation. And this can be used in many different scenarios. In the set of the slides that you can download from from the module, I have additional examples, and you might read through those examples to kind of further understand Little's law and then its application. Okay, and so this is an order for 16 units, right? And then this is some key observation. So I hope you will enjoy this topic, okay?